In this session, we're going to look at intercepts, vertical asymptotes, and holes. We are talking about rational functions, and for your reference, a rational function, for example, would be f of x is equal to x squared plus 5x plus 6 divided by x plus 3. In other words, a rational expression is a fraction that has a variable in the denominator, and a rational function is defined by such an expression. When we are getting to know a function, one of the things we look at is the domain. In the case of a rational function, the domain is going to be indicated by the denominator. Essentially, we're going to exclude values that make the denominator equal to 0. In getting to know a function for purposes of graphing, it's also good to know how to find intercepts. When we talk about a rational function, the X-intercepts are going to be indicated by the numerator, because X-intercepts are where y is equal to 0, and the only part that can make a fraction equal to 0 is the numerator of the fraction. We're also going to consider Y-intercepts, and Y-intercepts are where x is 0, and so we're going to evaluate the function at 0 to find the Y-intercept. So let's jot down what we can about this function here. The domain is going to be where the denominator is equal to 0. And so since our denominator is x plus 3, I know that x cannot equal negative 3. You see, that would make the denominator equal to 0. So I'm going to write down that the domain of this function is, in set notation, the set of x such that x does not equal negative 3. In trying to find the x-intercepts, I want to find the values that make the numerator equal to 0. And so I'm going to set x squared plus 5x plus 6 equal to 0. And since this is easily factored, we're going to go ahead and factor this. We get x plus 3 times x plus 2 is equal to 0, so x equals negative 3 or negative 2. We immediately have a contradiction. X equals negative 3 is not in the domain. But then I have supposedly an x-intercept at x equals negative 3. It's actually going to be the case that we don't consider intercepts before we reduce the rational expression. If we rewrite f as having a factored numerator, x plus 3 times x plus 2 over x plus 3, we see that the x plus 3's divide out. And f of x becomes x plus 2, but we have to remember that x does not equal negative 3. So what happens with the graph when x is equal to negative 3? I'm glad you asked. If we consider, just like y equals x plus 2, it's just not function notation, but it's the same thing. This is a line that has a slope of 1 and a y-intercept of 0, 2. But then we're already figured out that x cannot be negative 3. What happens at negative 3 is we have a hole. And so we end up with, we'll draw it as a little circle along that line. And that occurs when x is equal to negative 3. And again, here we have the hole. It's not going to happen very often, but holes come from variable factors that divide out. And I say variable factors because they are not like, just a 5 divides out. No, you've got to have a variable in the thing, in this case, x plus 3. Now I can see the x-intercept is at negative 2, 0. So let me scroll back up here and write that down. So after considering the reduced fraction, or rational expression, which is now, looks like a linear thing, but it's got a hole, I see when x plus 2 is equal to 0, then of course x is equal to negative 2. That gives us the x-intercept of negative 2, 0. As far as the y-intercept, as we said, we're going to evaluate the function at 0. And so in this case, f of 0, and I have it right here, x squared would be 0, 5x would be 0, and x in the denominator would be 0. Wait, you can't have a 0 in the denominator. No, the denominator itself cannot equal 0. X can equal 0, provided it's not a factor of the denominator. In any case here, f of 0 turns out to be 6 over 3, which is 2. And so we have a y-intercept at, in this case, 0, 2, which we saw in our graph. So let's peek back up where we started and recap what we just did. For the rational function, we looked at where the denominator was equal to 0 to indicate the domain of the function. And then we had to reduce the fraction, and then the x-intercept came from setting the numerator, or what was left, equal to 0. Finally, we evaluated the function at x equals 0 to find the y-intercept, and the domain, the x-intercept, and the y-intercept was the fruit of that labor. This is only part of understanding rational functions, but it's a good place to start, I think. In fact, what we just saw indicates kind of a step-by-step process that we can write down, but I don't think we're ready just yet, because what we have not yet considered is asymptotes. I like to appeal to things that we've seen when we're looking at something new. And so what I want to do is I want to remind you of the graph of y equals 1 over x, the reciprocal function. Since the reciprocal function has a variable in the denominator, that makes it a rational function. And as you recall, hopefully, if you don't, the picture's right here. There are two branches of this thing, one in the first quadrant and one in the third quadrant. And because of how reciprocals work, the branch in the first quadrant, as we get closer and closer to the y-axis, becomes larger and larger and larger, but it will never have a point on the y-axis, because on the y-axis, I know that x is equal to 0, and the domain of this is x such that x does not equal 0. So it's not that there's a hole, because nothing divided out. It's just that there's never a point on the y-axis. Likewise, in the third quadrant, this graph goes down, 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 but it never touches the y-axis. And that is characteristic of behavior near an asymptote. In fact, we call it asymptotic behavior. An asymptote is essentially a line that guides a graph. You kind of think of it as a center divider on a freeway. You can get really close to it, but you don't really want to touch it. As we can see, we also have the same situation as x gets larger and larger, the reciprocal gets smaller and smaller, but the reciprocal of a number won't ever actually be 0. As I said a moment ago, the only thing that can make a fraction equal to 0 is its numerator. Since the numerator is 1, 1 over x will never be 0. We see the same thing in the third quadrant. It's coming from below, but it's still going to be asymptotic with the x-axis. And so here we have two asymptotes. I'm not drawing them as lines because they aren't actually part of the graph, but they guide the graph. As it turns out, the vertical one, the y-axis, is what we call a vertical asymptote. The horizontal line that is coincident with the x-axis is called a horizontal asymptote. Now, the horizontal asymptotes are a topic for another video. The vertical asymptotes are things we're going to find in this video. Here's the deal. A vertical asymptote is indicated by the denominator, provided we have a reduced expression. So if I can scroll back up here, factors that divide out do not give us asymptotes. They do not give us intercepts. They give us holes. Factors in the denominator that help us to figure out the domain, in the case that they do not divide out, give us vertical asymptotes. We'll see how to find these as we go through our examples here. We'll see how they affect a graph in another video. So a moment ago I alluded to a step-by-step process for analyzing a rational function. This isn't the whole process, but these are going to be the beginnings of it. Now I'm numbering these steps at step 1, but they don't necessarily have to all follow in this order, but the first couple should be the first couple. Step 1, we're going to consider the domain of a function. And as we just saw, the domain is indicated by the denominator. After we have figured out the domain, step 2 is going to be reduce if possible, keeping in mind that factors that reduce lead to holes. After reducing, step 3, find vertical asymptotes. And vertical asymptotes come from problems in the domain, and so are indicated by the denominator again after the thing has been factored and reduced if possible. Step 4 is going to be to find intercepts. As far as intercepts are concerned, X-intercepts are going to come from where the numerator is equal to 0, because that's the only part of a fraction that can make a fraction equal to 0. And that's the same thing as saying finding out where y is 0. Remember, that's characteristic of X-intercepts. Finally, the Y-intercept, and that's going to be found by setting x equal to 0, evaluating the function at x equals 0. Notice when I say Y-intercept, there's only one, because to have two would violate the vertical line test. Let's get to work. Our first example, here we have f of x is equal to 2x plus 1 over x minus 3. Find the domain, vertical asymptotes, and intercepts of the function. First, we're going to find the domain. The domain, since the denominator is x minus 3, is going to be the set of x such that x does not equal 3. Remember, we don't want to zero out the denominator. This rational expression is reduced, nothing will divide out, so we can go straight to our vertical asymptote, which is going to be the vertical line x equals 3. As far as our intercepts, to consider the x-intercept, we're going to set 2x plus 1 equal to 0, the numerator of course, and 2x is equal to negative 1 as a result, and so x is equal to negative 1/2. And so the x-intercept, which I'm going to identify as, the x-intercept, is x is equal to negative 1/2, y is equal to 0, so negative 1/2, 0. For the y-intercept, we're going to evaluate the function at 0, so f of 0 is equal to, as I'm sure you can confirm, negative 1/3. Therefore, the y-intercept is 0, negative 1/3. Next, same instructions, domain, vertical asymptotes, and intercepts. The function is f of x is equal to 2x squared plus x minus 8 divided by x squared minus 4. The denominator, being x minus 4, factors into x plus 2 times x minus 2, and from these we get our domain. The domain being the set of values that don't zero out the denominator, we are looking at the set of x such that x does not equal plus or minus 2. I'm okay with the plus or minus here, that works for me. Now the numerator is not factorable, and therefore the fraction does not reduce. So the vertical asymptotes are obtained directly from the domain, essentially. Vertical asymptotes are going to be the vertical line x equals 2 and the vertical line x equals negative 2. As separate vertical lines, they should be written as separate equations. And so I don't want to see vertical asymptote x equals plus or minus 2. Don't do that. Go ahead and give me the equations of both lines. We turn our attention to intercepts. For the x-intercept, remember an x-intercept is where y equals 0. The only thing that can make this y equals 0 is if the numerator equals 0. So that boils down to setting the numerator, 2x squared plus x minus 8, equal to 0 and solving the resulting equation. Since it doesn't factor, I'm going to use the quadratic formula. So x equals negative 1 plus or minus the square root of 1 squared minus 4 times 2 times negative 8 all over 2 times 2. So we can say it's negative 1 plus or minus the square root of 65 over 4. That's fine to write as the points in the x-intercepts. We're going to say negative 1 plus or minus the square root of 65 all over 4, comma 0, our ordered pair. I'm okay with the plus and minus there. Just do me a favor, don't just be lazy with the asymptotes, that's all. By the way, if this radicand, which in this case is 65, had turned out to be negative, then it would have been complex numbers, and complex numbers don't give x-intercepts. And so if that were the case, we would say no X-Intercept, at least not from those factors. Finally, we're going to consider the Y-intercept, and remember the Y-intercept is going to be obtained by evaluating f at 0. The numerator being 2x squared plus x minus 8, if x is 0, is negative 8. The denominator being x squared minus 4, if x is 0, is negative 4. This reduces to 2, giving us a y-intercept of 0, 2. Next, we have same instructions. The function is r of x is equal to 3 times the quantity of x squared minus x minus 6 divided by 4 times the quantity of x squared minus 9. See if you can work through the 4 steps that I outlined earlier, finding the domain, reducing if possible, the vertical asymptote, or totes, and the intercepts. Find them on your own. Go ahead and pause the video and work it out. Okay, step by step here, starting with the domain. Since the denominator is 4 times the quantity of x squared minus 9, that factors into 4 times x plus 3 times x minus 3. And so the domain is the set of x such that x does not equal plus or minus 3. This time, we have a factor x minus 3 that divides out in the numerator and denominator. So our reduced form of our function expression is r of x equals 3 times the quantity of x plus 2 divided by 4 times the quantity of x plus 3. That leaves us only x equals negative 3 as the vertical asymptote. You see, when x minus 3 divided out, that would have caused a hole at x equals 3, which is the value that makes those factors equal to 0. On to the intercepts. For the x-intercept, we're looking where the numerator is equal to 0, and since the numerator is in factored form, 3 times the quantity of x plus 2, the x-intercept is negative 2, 0, that which makes the numerator equal to 0. And the y-intercept is going to be obtained by evaluating r at 0, which I can see is going to be 6 over 12, which reduces to 1/2. And so the y-intercept is 0, 1/2. So we're finding out a lot of information about these functions. Actually, we're finding out the same information over and over. But we're looking at a domain, vertical asymptotes, intercepts, in this case a hole. It feels like we're not doing anything. This is all part of analyzing rational functions. By the time we're done with this topic, we're going to use all of this information and more to graph these things. So I just wanted to make sure that we're okay with this part of the process, and then we're going to look at another part of the process in another video. On to the next example. Same instructions, domain, vertical asymptotes, and intercepts. The function is h of x is equal to negative 2 over x plus 1. Go ahead and pause the video and see what you can do with this. So the domain coming from looking at the denominator, I've got a denominator of x plus 1, and so the domain is equal to the set of x, such that x is not equal to negative 1. Because this is already in reduced form, I know immediately my vertical asymptote is x equals negative 1. Considering intercepts, since the x-intercept is what makes the numerator equal to 0, and the numerator is never 0 because it's negative 2, there is no x-intercept. It can happen. So we're going to write down x-intercept, none. For the y-intercept, remember we're going to evaluate the function at 0, so h of 0 is equal to negative 2 over 1, and so is equal to negative 2. So I'll just write down y-intercept, 0, negative 2. Last but certainly not least, domain, vertical asymptotes, and intercepts of the function r of x is equal to x squared minus 4x minus 5 over x minus 3. Go ahead and pause it, do your thing. So the domain being indicated by the denominator of x minus 3 is going to be the set of x such that x does not equal 3. Since the numerator in factored form is x minus 5 times x plus 1, we don't have a common factor, and so the vertical asymptote is going to be x equals 3. Again, that's coming from the denominator, issues in the domain that don't divide out. Intercepts. As far as the X-Intercept, we're looking at the numerator for that. We have it in factored form, so it should be fairly straightforward to note that the X-Intercepts are going to be 5, 0, and negative 1, 0, coming from the factors x minus 5 and x plus 1. The Y-intercept is going to be the function evaluated at 0. For that, I go to the original function. Seems a little easier to put 0 there. R of 0 is going to be negative 5 over negative 3, or 5/3, and so the Y-intercept is going to be 0, 5/3. That does it for this session.